Today we're going to look at momentum and collisions, specifically today momentum and impulse. So we're going to look at, what do you think? Imagine an automobile collision in which an older model car from the 1960s collides with a car at rest while traveling 15 miles per hour. Now imagine the same collision with a 2007 model car. In both cases, the car and passengers are stopped abruptly. So what about the newer car? What features in the newer car are designed to protect the passenger and the features designed to minimize damage to the car? So in the 2007 car, you're probably talking about airbags, maybe some seatbelt stuff. What about the design to minimize damage to the car? Made out of different materials and stuff. So think about how a collision would change or be different between those two situations. So what are the common terms for the momentum? You don't have to actually write a sentence, but think about how you use the word momentum in everyday. So in your examples, are you relating it to the velocity or the mass of the object? We'll talk about that and see what how your ideas change by the end. So momentum is symbolized by the letter. It's actually a Greek letter rho. Looks kind of like a P, but as rho is equal to mass times velocity. Momentum is mass times velocity, so it's proportional to both the mass. It is a vector. Since we're using velocity, it is a vector. And if you remember, vectors mean it has both magnitude and direction. And the SI units are kilogram times meters per second. So it could be, you could also call it a Newton times second, kilogram times meters per second, or Newton times second. So if we want to prove that these two are equal, okay, well, what is acceleration? Acceleration is the change in velocity over time. And mass times velocity, we just saw, is equal to momentum. So our force is equal to momentum over time, which is right here. Okay, so now if we want to look at impulse, impulse is really a type of measurement of momentum because the impulse is the force times your time interval, or change in momentum. So the change in momentum is also called impulse. So F delta T is equal to delta P, or delta rho. So your impulse is equal to your momentum. Here they have mass times final velocity minus mass times initial velocity, because momentum is mass times velocity. If we have a change in momentum, we have final minus initial. So the quantity F delta T is called impulse, and the SI units are Newton times meter, or a kilogram times meters per second. The impulse changes in momentum, and it's just another version of Newton's second law that we just saw in that previous slide. So change in momentum depends on both the force and the amount of time over which the force is applied. So if we have the same amount of force and we take longer time, it's going to change our impulse is going to be the same, but we can have, if our impulse is the same and we use a larger amount of time, we can have lower force, which is the whole basis of like airbags. They increase the amount of time that your same force is being applied on the front of the car, but the amount of time that you're actually in contact, instead of hitting the steering wheel, you're hitting the airbag, so it decreases the force. So let's see what we have here.
A truck filled with heavy bricks is harder to stop than an empty one. This is true even if the trucks are traveling at the same speed. The heavier truck needs to start putting on the brakes when it is much further from the stop sign. Using Newton's second law, we see that the truck with the larger mass will have a smaller acceleration. We can also use the impulse momentum theorem to understand the situation. Both trucks use the same braking force and have the same initial and final velocity. However, due to its larger mass, the momentum of the second truck is larger. If the applied force of the brakes is the same, we see that the truck with the larger momentum will require more time to change its momentum. The quantity force times time is called impulse, and it is equal to the change in momentum.
Okay. So greater changes in momentum require more force or more time. So it requires more time to stop. The greater momentum, the change in momentum for the truck with more mass. Oops. So we have the same stopping force. So if we have the same stopping force, we have to have more time to stop because we have more momentum with the larger truck or the heavier truck. So we can go ahead, let's think about this problem. If we have a 1,350 kilogram car and it has a velocity of 22 meters per second to the north, when the braking rapidly, it stops in 4.5 seconds. What's the momentum of the car before braking? Okay, momentum is mass times velocity. So we could take just the mass of the car times the velocity of the car to get the answer there, and then the magnitude of the force required to stop the car. Well, our change in momentum, if we're starting at 22 meters per second and going to 0, our change in momentum is going to equal to the momentum we just got here, the 1350 times 22. So we can say force times delta t would be 4.5 seconds, is equal to our change in momentum, which is what we got here. So we could solve for force then. So our answers should be 2.97 times 10 to the 4th kilogram times meters per second to the north, and then 6.60 times 10 to the 3rd newtons. Can check those answers. Okay, stopping time is just the time needed to stop. So increasing the time would decrease the force. If we increase the force, we would decrease the time. They're inversely proportional there. So what examples demonstrate this relationship? Airbags. So airbags, we already kind of talked about, will increase your time, which would decrease the force on your head in a collision. Padded dashboards, trampolines, you're increasing the time that you're actually in contact with the ground, so it decreases the force. Think about if you were jumping that high on the ground, the impact on your legs and your body compared to on a trampoline. Decreasing the time increases the force. So what examples demonstrate this? Hammers and baseballs are used a hard material to reduce the time of impact to create an increased force. Also think about in a collision compared to an airbag, if your head were to hit the steering wheel, your time now is decreased and the force on your head would be much greater. Okay, if a 65 kilogram passenger in a car travels at a speed of 8 meters per second, the passenger is stopped by an airbag in 0.75 seconds. How much force is required? We can use force times delta t is equal to the change in momentum. So our momentum, our change would be going from 8 meters per second to 0. So if we, our change in momentum would be equal to our initial momentum, basically. So we have mass of 65 times 8 meters per second. We have force equal change in time would be 0.75 seconds equals our 65 times 8, and we should get 6.9 times 10 to the 2nd newtons. If the car does not have an airbag and the passenger instead is stopped in 0.02 seconds when he strikes the dashboard, by what factor does the force increase? Well, the force is now 2 times 10 to the 4th newtons, so that's 29 times greater. You would solve that problem just the same way we did that first one, but you can see that force has changed dramatically. Here's a couple extra sample problems if you want to go through You can pause it here and try these problems. And here's another one you can pause about the snowmobile, looking at change in momentum and the magnitude of force. And finally another one. And pause here if you want to have more practice. So now what do you think? We've already talked about collisions in automobiles a little bit through the lecture. Between an automobile in the 1960s and 2000s, how would the features of the car designed to protect the passenger in the car? And then what is the difference between momentum and impulse? Really, they're the same. The change in momentum is equal to impulse. The impulse is the force times change in time. Momentum is equal to mass times velocity. Now you could also, I'm going to just give this little equation as F delta T is equal to as the impulse, and that's equal to change in momentum. We could also have change in momentum equal M delta V. So we could have F delta T is equal to M delta A. That's one way you could also write that equation.